Hello, welcome to this second part of my series of lectures, which are entitled Gravitation and Electromagnetics, Similar as Varies. My name is Schwarzschild, and in this second part, we will make an application of general relativity in our approximation scheme, which is low velocity, weak interaction. The first part then here of these applications. So I split it into A and B. So first here today, or in this lecture, we consider parallel motion, which is the simplest possible interaction where kinematical effects appear. So to get acquainted with this for this general relativistic equation, we then study gravito-magnetism. And then the main thing in this lecture is to derive the perihelion shift, and that is actually due to, in force perspective, to gravito-induction. Then in next lecture, we will start the length stealing, frame dragging, and also geodetic precession, which is measured by a satellite experiment, gravitation probe B. It's an amazing experiment. So let us repeat first from part one. We learned the following: that general relativity can be expressed in the force perspective with this formula here. And then we consider the mutual interaction between two objects, number 1 and 2. They have arbitrary velocities, which may change in time. So notation here, 1 on 2 means we study force on number 2 in an interaction with number 1. This force perspective, this formula, that's also called the first post-Newton correction in general relativity. It's valid up to order v squared over c squared. And these are kinematical correction to the static Newton force formula here. And we shall interpret this as kinematical corrections, as I said. So we have something depending on velocity here. And that is then called gravito-magnetic, to borrow terminology from electrodynamics. And we also have an acceleration-dependent term here, where force on number 2 depends only on acceleration of object number 1. Whereas the magnetic force here depends also on the velocity of number 2. So force on number 2 depends on which velocity number 2 possesses. We compared last time with electrodynamics, and we found a striking, I would say, similarity where kinematics effects have the same structure. So velocity and acceleration here appear with the same structure. We have a 1 over distance dependence on the inductive term in both cases, 1 over distance squared for the magnetic in both cases, and 1 over distance squared for the static. This means that we can take over the calculational methods that we have learned from electrodynamics. We can take it over to general relativity. So we make some obvious replacement of the sign of the terms, and also this spurious factor 4 we have here in gravitation. Nobody knows where it comes from. It's anyone is welcome to do research on that interesting factor. And we also have to replace charge with mass and the coupling constant, of course. This is not action at a distance as some people think, especially all those brilliant physicists working in curved space-time picture, because this is really it's a force mediation. So you can think of that the force here is mediated by the graviton, by the photon, respectively. And the mediation speed is speed of light. So that's why speed of light appear here. Because of this finite mediation speed, we get this kinematic correction. That's why they call kinematic correction. Had speed of light been infinite, so instantaneous action at a distance, then we put c equal infinity and the kinematic correction disappear. So let us now go to the simplest possible interaction, which gives a kinematic effect, and that is the parallel motion. So velocities then are perpendicular to distance vector r, and there is no acceleration. So this green term here vanish. So I shall emphasize that green color means inductive, red color magnetic, and blue color means static, just to make it easier for you to distinguish between the effects. Now, in this parallel motion, as I said, velocity is perpendicular to distance vector. And that means that this term here vanish, this magnetic term vanish. The magnetic effect is controlled by this term. The velocities are in the same direction, and we also put equal magnitude, so we get the v squared from here. So the force is a static force, and then minus v squared over c squared times this factor here. Same thing for electrodynamics, exactly the same analysis. So you see, we have a completely parallel calculational method in the two cases. So the result of that is given here. Parallel motion, equal velocity. We have an extra factor 4 here. Kinematics effects are enhanced to factor 4 in gravitation compared to electrodynamics. Red means magnetic effect, so this is what people often call magnetic force. To me, kinematical corrections are not a force, but they are correction to the force. So there is a static electric and gravitoelectric force, and what we see here is the modification of that force due to kinematics. But it doesn't matter. You can call it force if you like. You can call it magnetic force and inductive force. In electrodynamics, we know actually, although you must remember we have derived this, both these formula in low velocity weak interaction scheme, because electrodynamics is inferred from experiments taking place at that approximation. First of all, we note that at low velocity, in electrodynamics, velocity, I mean, is 1 millimeter per second. So this is like a 10 to minus 23 correction. So it's not measurable. And the same thing here, even if you can have speeds of the masses here of 100 meter per second or so, yeah, this term is extremely small compared to this. So this is not observable in gravitation, but in electrodynamics, this is observable. And that is because we can do it in closed conductors, which are the miracle of nature, because there we have so many conduction electrons, like 10 to 23 or so. Remember, this is what 10 to minus 23, but we have 10 to 23 conduction electrons in order of magnitude. That's the Avogadro number. So that is amazing, I think. So, and they all work in the same direction. So that's why we can see this magnetic effect in closed conductors, which are really a miracle. Also, we have in electrodynamics additional information, and that is from particle accelerators. Then we accelerate also many particles in bunches, and they travel at parallel velocity, and then they actually reach almost speed of light. So we have a high velocity measurement also in very special circumstances. And it turns out that this formula happens to be valid also in that case. So that's a coincidence, of course. And then you see when we approach speed of light, the electrodynamic force vanish. And as people say, that's because the magnetic force equals the electric force. Yeah, so they cancel. So this term here equals that term here. And that is actually very important for technology of particle accelerators because that's the condition for their operation. If this force didn't vanish, then the particles of the bunch would repel and the beam would decay. We wouldn't get a stable beam simply. So this is a very interesting statement and observation, of course. Now we go to gravitation here, and then if we apply the same condition, high velocity, then something spurious would happen, that the force between them change direction. This can be shown is not allowed in nature because that would contradict the principle of cause and effect. Principle of time would run backwards. So that would be a blow for general relativity, of course, if it predict such a phenomenon. But we are saved because we work in low velocity, so we are not approximation. So we are not allowed to go to that high speed. So far, no problem. Still, that factor 4 is really, really, really interesting. If someone find out where it comes from, please inform me about it. So that was a warm-up. Now we go to a phenomena that can be observed and has been observed and measured accurately. And that is the planetary perihelion shift, and in particular for Mercury. So this is what is observed for the orbit of Mercury is that the nodal direction shifts, and with that, the position of closest approach to Sun shifts. So that is what the perihelion shift means. And it has been measured actually over 100 years ago. So it was well accessible to Einstein 100 years ago. So this shift here has been measured. Now there are many perturbations to the planetary motion, as you know, and if everything is taken into account, there is still a remaining significant perihelion shift that cannot be explained with Newtonian gravity. So that was Einstein's mission to check whether general relativity could account for that missing part. And that was the first calculation he did. It was the first verification of general relativity because, as you know, Einstein really got the correct perihelion shift. After some errors, but finally he got it. And then in our perspective, Einstein worked in the curved space-time perspective, so he found first a metric around the sun, and then from that he could derive the equation of motion of Mercury, and from that he calculated the perihelion shift. But our perspective is different. We use the force perspective. We use the equation that Einstein himself has derived. So one can then wonder, why didn't Einstein use the force perspective? That was because the force formula was derived much later. So then there is a very interesting article here, which is a kinematical analysis of central force motion. And what they show there in that paper, that is how must the Newtonian gravity force change in order to obtain the perihelion shift that is observed. The missing shift that cannot be calculated by the gravitational force, the Newton force. They found the correction has to be this term here. So it's a v squared over c squared, so it's in our approximation scheme. And it's a tiny correction. The velocity of Mercury is not so high, so it's a very tiny correction. So we write it out in two terms. So here is the Newton gravitational force, and here is the correction. And you see there's a plus, they have opposite sign, there's a plus sign here. So this is a tiny, small outward pull. So I can describe it graphically here. So we have the Sun and Mercury, and this is not drawn to scale. Mercury is much smaller, and you know Mercury is orbiting at about 100 solar radius from the Sun. So it's much far away. This green force here is much smaller in reality than on picture. So I have used the green color here, meaning that what we will show that this is an inductive effect, gravito-inductive effect. Object number one is the Sun. Object number two is Mercury, or the planet in general. This is the total force on Mercury in the interaction with object number one, which is the Sun. There is a force on the Sun too, due to Newton's third law. So it is given here. And that is very important for our analysis. In our analysis, Sun cannot be static, as Einstein assumed. Einstein assumed a static Sun, a non-rotating Sun. Here is this description, the difference between the approaches. Einstein's approach is a static Sun. He derives the metric for a static spherically symmetric object. He derives it himself. It turns out to be the Schwarzschild metric in approximate form, so low speed, weak interaction. So that is the approximation scheme Einstein uses. It's the same approximation that we use, and it's a valid approximation, of course. So, but in our perspective, field-free interaction approach, there can be no general relativistic effect if we assume the Sun to be static. Because general relativity in this approach, we go back, are kinematical effect. If Sun is static, V1 is 0, acceleration here is 0. So all kinematics vanish, general relativity effect vanish. So we need a motion on the Sun, and that motion can be, that is what we will check. We have to take into account that Sun is not static, but it accelerates radially around the center of mass, so-called barycenter. This acceleration is, of course, tiny, but we look for a tiny effect. So we have a radial acceleration. So that's an inductive effect, a gravito-inductive effect. The acceleration of the sun gives a gravito-inductive force on Mercury. And our hypothesis is that that is this extra gravitational pull that is needed. We have to do the calculation to check. There's another motion which Einstein neglected, and that is the spin of the sun. We have calculated that too. We will not show it here, but that will give a gravito-magnetic effect. So the velocity of mass elements of the sun, that is due to the spin of the sun, interact with the motion, the orbital motion of Mercury. That is negligible. Why? Remember, Mercury is about at a distance 100 solar radius from the sun. So we have a motion in one direction on this side of the sun and the opposite direction on the other side. So that will cancel. So the net effect of that is very, very small. It's completely negligible. It's completely negligible. So the only candidate that remains is the gravity-inductive force. So that is what we shall analyze now. So we start with the equation that we wrote down before. So this is a full general relativity in the low velocity weak interaction approximation. We follow the same scheme as the reference I mentioned earlier, and that is to put this factor here, which is the interaction energy. So it's the increase of mass of M2 due to gravitational interaction. And that we discussed in the last lecture, that is equivalent to the gamma factor, special relativistic gamma factor. So, which it must be, because we know left-hand side is the time derivative of relativistic momentum. We put that factor on the right-hand side, so we interpret it as a source to the force. So we divide by this factor accurately, then this factor should be put inside the time derivative, but it doesn't depend on time, really. We can neglect the time dependence here, that's why I put it outside. We divide it so that it appears on the right-hand side. We make a Taylor expansion, so 1 plus will be 1 minus. Then it appears only here in the static term, because for the other two effects, we will get terms 1 over c to the fourth power, and that we neglect. So this is our new force. We have redefined force now. So we have a Newtonian force here as what they deal with in this reference. Then next step is to neglect the red one, because that is the magnetic effect, and as we motivated before, it is negligible. We have calculated it, and other people have calculated it. It's negligible. So this is what we end up with for the force on Mercury, the planet number 2. Everything seems to be treatable apart from this acceleration here. Number 1 is the sun, so this is the acceleration of sun, and we don't know that. So how can we get it? Well, we can use Newton's third law. So we apply Newton's third law. So this formula here, this formula is written out for our force. It's written out here. And then instead of acceleration of Sun, we have a right-hand side acceleration of Mercury. So an acceleration of Mercury, or the planet in general, is just v squared over r in our approximation scheme. That's a centripetal force. So what we then do, we solve this equation for acceleration of Sun. And then we get a complicated expression, but most terms here are of the order 1 over c to the fourth, that we can neglect. Solving this equation for the dv1 dt, we insert that here. We neglect everything which is higher powers than 1 over c squared. So there is some algebra behind this, but it's easy. I mean, it's elementary algebra, so you can do it yourself. So I will just show the result now when everything is done. And the result is, of course, it was a very happy moment of my life, as Einstein, an expression Einstein once used. And it gives this force. This is the force that will give the observed perihelion shift. We go back. What I have used then is the result from this reference here. So it's exactly this force that we obtain in our analysis and the force perspective. Also, what we in addition obtain in the force perspective is the contribution of different effects, because we do not only have inductive effect here, we have also effect of the gravitational energy. And it can be shown that gravitational energy term contributes 25% to the perihelion shift. And this is not easy to obtain in the space-time perspective. But here it's straightforward. So it's not only the inductive force which causes the perihelion shift, but it's also this general relativistic factor of gravitational energy. So then finally, we can discuss how is it possible that Einstein's calculation, assuming a static sun, how can it give the correct result? How can it give the dynamics? How can these two approaches be equivalent? Well, it's because of the equivalence principle, stating that static gravitation is equivalent to acceleration. Well, this is a nice demonstration of the equivalence principle. So that was the first part. Thank you very much for listening. Now I will make a separate video for the second part of these applications and discuss the so-called dense theory frame dragging, and that is a gravito-magnetic effect in the force perspective.